So we will now begin the fifth major phase of this course, talking about matrix determinants and the different things that they can be used to do in a linear algebra context. So the next several lessons will be focused on square matrices as opposed to rectangular matrices and their determinants. So in this first lesson, I would like in particular to focus on how to calculate determinants of matrices, of rather large matrices, matrices that might be 4 by 4, 5 by 5, etc. And in establishing that process, let me start by going back and reviewing a little bit from our lesson on matrix arithmetic right at the very start of the class. In our lesson on matrix arithmetic, right at the very start of the class, we established a method for 2 by 2 matrices and for 3 by 3 matrices. For example, for 2 by 2 matrices, we said, okay, move along the top row, extract the entry in the upper left corner, and then block out that row in that column and multiply the entry 1 by this value that was left after that blocking out process was completed. So multiply 1 by 4. Then move to the next entry in that first row, the number 2, extract the number 2, then block out the row and the column containing 2. And that leaves behind this 3 in the bottom left corner. So multiply 2 by 3. Then go between the terms and alternate, plus minus. So we have in this case plus 4 minus 6, result negative 2. We used a very similar process when doing the determinant of a 3 by 3 matrix, right? Here we started by extracting entries along the top row, 1, 2, 3. Then we blocked out the row and the column containing those entries. We extracted the submatrix that was left behind after we did that blocking out, and we multiplied the entry by the determinant of that submatrix. And then we alternated the terms plus, minus, plus as we moved between those terms there. So the alternating process. So perhaps you can guess how we might approach calculating the determinant of this 4 by 4 matrix. Someone says find the determinant of the following 4 by 4 matrix given here. I'm going to start, for example, in the top row in the very first entry, extracting the value 0. I'm then going to block out the row and the column containing that 0. And I'm going to look at the 3 by 3 submatrix that's left behind. So that gives me 0, 1, 0, 2, 0, 3, and 0, 0, 0. Then I'm going to move to the next entry in the top row, this value 1, and I'm going to extract it. And then I'm going to block out the row and the column containing that 1. And I'm going to look at the 3 by 3 matrix that is composed of all the entries that are left behind. So it looks like I get the matrix 0, 1, 2 in the first column, 1, 0, 0 in the second column, and 0, 3, 0 in the third column. I'm going to do the same thing with the entry number 2 here, the next entry in the top row. Extract a value of 2, and then cross out its row and column, and then extract the submatrix that's left behind. So we have the determinant of 0, 1, 2, 0, 2, 0, and 0, 0, 3. And then finally the last entry, 0 in the top row, extract 0 and then block out its row and its column. So that would be 0 times the determinant of 0, 1, 2 in the first column, 0, 2, 0 in the second column, and 1, 0, 0 in the final column. Having extracted those entries, you would then go through the terms and alternate the first term plus, the second term subtracted, the third term added, and the fourth term subtracted, plus minus, plus minus. So all that would be left to do at this point would be to actually calculate these 3 by 3 determinants, right? Calculate each of these 3 by 3 determinants, and then those unpacked and unravel into a succession of 2 by 2 determinants. And actually, as wild as it sounds, I'm going to go through this process with you because I want us to sit with how useful it is that this matrix has so many zeros inside of it. For example, because this top row had two zeros, immediately two of these terms in this expression vanish, right? This 0 times this first determinant is gone. This 0 times this final determinant is gone. Boop. Now, let's think in particular about what would happen with this third term. Let me zoom in on this third term for a minute and think about what it would look like to calculate the determinant of this 3 by 3 matrix. Notice that all of the entries in the top row are zeros. So the determinant of this 3 by 3 would become 0 for sure, right? And so that would eliminate this middle term as well. So ultimately, that only really leaves me with this middle term here that might potentially produce something non-zero. So let's go ahead and copy down this middle term to the next line. And let's work on expanding this determinant. On the outside, I have here -1, big set of brackets for this 3 by 3. Now, as I expand again along this top row, I encounter here this 0 in the first position. So that's going to give me a 0 from that term, no matter what is happening down here in the bottom right corner. Then next is another copy of -1 times the determinant of the submatrix that is formed by blocking out that entry. So 1, 2, 3, 0, read in terms of the columns. And then another 0 in the back because this 0 in the third position of the top row will just eliminate everything. So what's left? What's left is -1 times -1, that's +1, and then the determinant of this 2 by 2 matrix here in the center, which will become 0 minus 6. So the overall determinant of this 4 by 4 matrix is -6. That is the process for calculating determinants of larger matrices. It's recursive. It kind of unwraps like a nesting doll, where a 4 by 4 determinant becomes a series of 3 by 3 determinants, and each of those 3 by 3 determinants becomes a series of 2 by 2 determinants. That's the overall process that we use for larger matrices. And in particular, if you're lucky enough to have a matrix that has tons of zeros inside of it, what we sometimes call a sparse matrix, then calculating the determinant of even large matrices can be straightforward because a lot of the terms vanish during the calculation. So with that in mind, let's talk about what are called diagonal matrices and what are called triangular matrices. So if you have a square matrix that's called diagonal, a diagonal matrix is only allowed to have non-zero entries on its main diagonal. So let me show you what I mean. A matrix of 1, 2 on the diagonal and zeros elsewhere, this is a diagonal matrix. A matrix of -3, 0, 0, 0 is also a diagonal matrix because all of its non-zero entries are on this main diagonal. The only non-zero entry is -3, but it is on this main diagonal, so that counts. Let me give you some non-examples. If I gave you a matrix that had non-zero entries on this opposite diagonal, going from bottom left to top right, this would not be considered a diagonal matrix. If your matrix only had a single non-zero entry, but it was located up here in the top right, that would not be considered a diagonal matrix. And if your matrix has, mostly non-zero stuff inside of it, like 3, 4, 2, -1, this of course is considered not diagonal as well. So diagonal means that if you have any non-zero entries in the matrix at all, they are all located along this band going from top left to bottom right. Similar to that, we can talk about matrices that are called upper triangular. Upper triangular matrices are allowed to have non-zero entries on the main diagonal, but also above it. So something, for example, like 1, 2, 3 in the top right corner, 0 in the bottom left corner. This is something that would be considered upper triangular. By contrast, lower triangular is allowed to have non-zero entries underneath the main diagonal. So something like 1, 2, 0 in the top right, and 3 in the bottom left is considered lower triangular. So diagonal means non-zero entries are on the diagonal only. Upper triangular, they can be on the diagonal or above. Lower triangular, they can be on the diagonal or below. Now, as it turns out, when you're working with a diagonal matrix, or when you're working with an upper triangular matrix, or when you're working with a lower triangular matrix, you can calculate their determinants very, very easily as a result of all the zeros that are present in that matrix. Let me give you a demonstration with this 4 by 4 matrix here, this 4 by 4 lower triangular matrix. Someone says, find the determinant of this guy. Okay, well, if I go through the 4 by 4 determinant method, I would start by extracting this value 1 in the upper left position here. And I would multiply that by the determinant of the 3 by 3 matrix left behind. Now, in theory, I would write the other 4 terms in this expansion, but notice that the other 4 terms in this expansion would all vanish, right? Because it would be 0 times something, 0 times something, 0 times something. So those are definitely not going to contribute anything to this determinant. So all that matters is what's happening with this first entry. So now let me think about what's going on with this 3 by 3 determinant that I have extracted. If I wanted to calculate this 3 by 3 determinant, once again, I would start with this position in the top left here, 5. And I would multiply that by the determinant of the 2 by 2 submatrix left behind when 5 is blocked out. But once again, because of the zeros in the second and third position, that would be the only non-zero term in this determinant. The other 2 terms would be destroyed by these zeros. So I can close up those brackets. This is all that contributes meaningfully. But now look inside of this 2 by 2 determinant. Once again, only the very first entry here matters. Only the 8 actually matters, because the second entry of 0 is going to just destroy the term that that 0 would touch. So I'm left in the end with 1 times 5 times 8 times 10. 1 times 5 times 8 times 10. Let's compare that result to what was happening in the original matrix I was given. The values 1 and 5 and 8 and 10 are the values that are showing up on the diagonal of this matrix. 1, 5, 8, 10. So what we see is that the determinant of this lower triangular matrix, the determinant has worked out to be the product of the entries on the diagonal. And that property turns out to hold both for lower triangular matrices, as we've explored in this example, but also for upper triangular matrices and for diagonal matrices. So let's go ahead and summarize that result. If you're dealing with a square matrix, and that matrix is diagonal or upper triangular or lower triangular, the determinant of that matrix can be calculated by multiplying the entries on the diagonal. So that concludes today's video on calculating determinants of larger matrices. We learned that determinants of larger matrices can be calculated using the same basic recursive process that we learned in the matrix arithmetic video. If you're lucky enough to have a matrix that is diagonal, or a matrix that is upper triangular, or a matrix that is lower triangular, then you're really lucky because the determinant can be calculated very easily. The determinant of a diagonal or triangular matrix can be found by just multiplying together the entries that appear on the diagonal of that matrix.